7.4 Inverse Matrices. Our learning intention, how to find the inverse of a matrix, and as our success criteria, I can find the inverse and determinant of a matrix. The identity matrix. The number 1 is called the multiplicative identity because the original number remains identical to what it was before the multiplication. For example, 3 times 1 equals 3, 17 times 1 equals 17. So that original number, that 3 and that 17, does not change when multiplied by 1. The equivalent matrix to the number 1 is the identity matrix. A square matrix, note the word that it's, let me change that to red, it's square, with all the elements in the leading diagonal. So leading diagonal is from this top left-hand corner down, excuse my not very straight arrow, are 1 and all other elements are 0. So that should say elements. I think I fixed it up in the PowerPoint. All other elements, there we go, are 0. So everything else other than that leading diagonal is 0. Multiplying a square matrix, so we need to multiply it by another square matrix, by the identity matrix leaves the original matrix unchanged. I'm going to show you in the next page or two. The inverse of a square matrix A, written as A to the negative 1, is the matrix where A times A to the negative 1 equals A to the negative 1 times A equals I. All right. Think about when you have negative powers. That A to the negative 1, when you're talking about the index laws, A to the negative 1 is actually 1 on A. So if you did A times 1 on A, you'd end up with A on A, which is equal to 1. All right, let's keep going. So example 8, which is, let me just double check what page I'm on in my textbook. I think I'm on about 31 if you're following along. If A equals a 2 by 2 matrix, 3, 10, 2, 5, and I is the identity matrix, find AI and IA by hand. All right, I'm going to do these in different colours. I don't like that red. I like that red better. And we're going to go blue for starters. So A times I is, AI is equal to, so note that the A is first, so I do the A matrix first. And my I matrix, my identity matrix, I put my 1s down my diagonal, and then I fill the rest in with zeros. And then I multiply through. So using that same method we learned in multiplication of matrices, back to blue, we go across first. So we go 3 times 1, 10 times 0, and we add them together. Then we do 3 times 0 plus 10 times 1. So we're now doing that, still that top row and that second column. And then we have, 0 times, so, no, we're not 0, I'm using 2. Wrong number. Onto my bottom row. 2 times 1 and 5 times 0. 2 times 0 plus 5 times 1. Put a square bracket around it all. Let's simplify. So 3 times 1 is 3. And 10 times 0 is 0. So 3 plus 0 is still 3. 3 times 0 is 3. 10 times 1 is 10. I'm going to write these numbers in red so you can see what they are. So that's 3 plus 0, 0 plus 10, 2 plus 0, 0 plus 5. That makes it easier. So 3, 10, 2, and 5. Ta-da! So I still end up with matrix A. So if you compare that to what's up the top there, exactly the same. I'm going to go into a dark green. That'll at least be enough difference. Now we're going to go I times A. We're going to do it the other way around. So we put our identity matrix, and then we put our original matrix, which is 3, 10, 2, and 5. Now again, going across the top and then down that first column. And we're doing 1 times 3 plus 0 times 2. Then we do 1 times 10 plus 0 times 5. So I'm now going down that second column, still using the same top row. And then the second line I'm using the bottom row, which is 0 times 3 plus 1 times 2, and 0 times 10 plus 1 times 5. You don't have to get these absolutely perfect this year. You do next year. It's taken me a full year to figure it out and get my head around some of these things. So 1 times 3 is 3, plus 0 times 2 is 0. 10 plus 0, 0 plus 2, and 0 plus 5. Now we put that into a matrix at the bottom and we end up with 3, 10, 2, 5. Ta-da! We have the same thing. Now, the identity matrix, this AI equals IA equals A, this is an example where we can change the order of the matrices and the product still stays the same. So normally with matrix multiplication, AB does not equal BA, whereas, but with the identity matrix, we can switch it around, it doesn't change. All right, the inverse matrix. The multiplicative inverse of the number 5 is 1 on 5. That is, when you multiply 5 by 1/5, you end up with 5 on 5, which equals 1. The multiplicative inverse of a matrix is what you multiply by the original matrix to get the identity matrix. The inverse of a square matrix A, written as A, oops, that should be a to the negative 1, my error, written as a to the negative 1, is the matrix where a times a to the negative 1 equals a to the negative 1 times a equals I. All right, hang on a minute, I'm going to write this out. So instead of using, as I said on the previous slide, a to the negative 1, instead of using 1 on a, we use this guy up here, a to the negative 1. Instead of going a to the negative 1, we just call it inverse. Inverse A. Saves a lot of time, saves a bit of mouthful. Imagine if you kept on having to say the multiplicative inverse or the a to the negative 1. No, that's not going to work. It's too confusing. Stick with inverse A. So A times 1 on A gives you A on A, gives you I, or 1. Okay, example, I'm moving on to page 32 if you're following along. Show that the product of two matrices equals the identity matrix. So show that the matrices 3, 7, 2, 5 and 5, negative 7, negative 2, 3 are inverses of each other. So it means show that the product equals the identity matrix. Go back to blue, it's a nicer colour to work with. Okay, so let's start with multiplying. 3, 7, 2, 5, 5, negative 7, negative 2 and 3. Now I'm going to say I actually cheated because I did this last year, so I still had it in my notes. I've got all the workings out. And again, first we do across there, we do down there. I'm going to colour code this. So 3 times 5 plus 7 times negative 2. Then we still use that same row and we go down the next column, which is 3 times negative 7 plus 7 times 3. We'll go to orange. Now we move to the bottom row. So we go in that bottom row and still and back to that first column. So we've got 2 by 5 plus 5 by negative 2 and purple. Bottom row, second column. So we have 2 by negative 7 plus 5 by 3. All right, so I'm going to solve each of those. So So 3 times 5 is 15. 7 times negative 2 is negative 14, so we take 14. 3 times negative 7 is negative 21. 7 times 3 is plus 21. 2 times 5 is 10. 5 times negative 2 is negative 10. 2 times negative 7 is negative 14. 5 times 3 is 15. Put some equal signs here. Now we just go from there. 15 take 14 gives us 1. Negative 21 plus 21 gives us 0. 10 take 10 gives us 0. Negative 14 plus 15 gives us 1. As easy as that. So we've shown that the product of the two matrices equals the identity matrix. We can, did I leave room for it? No, that's okay. We actually have the ability to switch it around the same way and we still end up with exactly the same number. Whether you go 3725 times the second matrix or do the second matrix times the first matrix, in this instance you will still end up with the identity matrix. Finding the determinant and the inverse of a matrix. So the determinant is very straightforward. To find the inverse of a matrix, we first need to find the determinant. Starting with only 2 by 2 matrices, as the calculations involved for finding the determinants and inverse of higher order square matrices 3 by 3 and 4 by 4 are significantly more complex and require a CAS calculator. I need to put a full stop in there somewhere, but don't worry about it. All right, so what we do in Year 11 is all we work through is 2 by 2 matrices. So we have our matrix A, this guy down here. We have labelled each of the elements A, B, C, D. So I'm not worrying about numbers at the moment, just A, B, C, D. The determinant is written as det in bracket A, where AD, so that's A times D, minus BC, B times C, is equal to that determinant. And what we do is we use these numbers here. So for example, if my matrix was 1, 2, 3, 4, I would have number 1 in position A, number 2 in position B, number 3 in position C, and number 4 in position D. Then I would substitute those numbers into the matrix, into the formula. So in this case, we've got 1 times 4 take 2 times 3, 4 take 6 equals negative 2. You know what? It's perfectly okay to have a negative determinant. Then what we do is to find the inverse, which is our next step, this 8 and the negative 1 on the left-hand side. We do 1 over ADBC, which is 1 over the determinant. In this case would be 1 over negative 2. And then we make a couple of changes. So I'm going to get rid of those guys there. So what we do is, where's my highlighter? Yellow is pretty light. Okay, so we take A and D and we switch them. Then we take B and C and we negative them. Now, if it's already a negative, we make it a positive. If we had the matrix 1, 2, 3, 4, we would end up with 4, 1 in the opposite corners because we've switched them, negative 2, negative 3, and then you put this guy at the front. Now, one rule, the inverse, when it doesn't exist, is when the determinant equals 0. So if you've got a problem and it asks you for the determinant, then the inverse, we can only find that inverse if it is a whole number. So positive or negative number doesn't matter so long as it is a non-zero number. All right, some examples for the determinant and the inverse. Following through, I'm on page 33 if you are keeping up with things. For the following matrices, find the determinant and the inverse if it exists. So our matrix in this case is A equaling 6, 2, 8, 3. So first of all, we'll find our determinant. Determinant of A is equal to, AD minus BC. I write this out a few times so I can just reiterate and I can also show you what's going on. So remembering, this is my A, B, C, D. So A is 6, D is 3, then we subtract B being 2 and 8 being C being 8. 18 minus 16, my determinant is 2. Okay. So the inverse, what I have to do first for my inverse, easiest way to do it is to have a look and switch what I need to. So I've got D, A, negative B, negative C, which is, in this case, D, which is 3 up in the top left-hand corner now, and 6 down in the bottom right. My B, which is 2, I would switch that to negative 2, and my 8, I would switch that to negative 8. Then I would multiply everything by 1 over the determinant of A. Now remember, our determinant down here on the left is 2, so 1 over 2. So in order to find the inverse, all I do is then use scalar multiplication and multiply all of that through each element. So a half times 3 gives me 3 on 2. A half times negative 2 gives me negative 2 on 2. I will simplify it. Negative 8 on a half. And that shouldn't be negative. That was a bump. Sorry. 6 on 2. So simplifying 3 on 2, can't do, so we keep it. We try to keep things in fraction form as well rather than moving them into decimal form. Negative 2 on 2 gives us negative 1. Negative 8 on 2 is negative 4. And 6 on 2 gives us 3. This is the inverse. Now, if I was to multiply this inverse matrix by this original matrix, I would end up with the identity matrix. I'm not going to go into detail and show you how to do it, but just trust me. Still continuing with example 10. Again, finding the determinant and the inverse if it exists. So my matrix here, my matrix is, for B is 2, 5, 3, 7. Determinant of B is equal to AD minus BC. My A is 2, my D is 7. My B is 5 and my C is 3. 14 minus 15 gives us negative 1. That's a really easy determinant to deal with. Now the inverse. Again, we're switching our A and D figures, and we're making our B and C negative. So I've got 7 in the top left, 2 in the bottom right, negative 5, negative 3. Box around those. 1 over, now my determinant was negative 1. 1 over negative 1, which 1 over negative 1 gives us negative 1. 1 over 1 is 1. So all I need to do now is multiply everything within my matrix by negative 1. So 7 times negative 1 is negative 7. Negative 1 times negative 5 is 5. Negative 3 times negative 1 is 3, and negative 1 times 2 is negative 2. That is my inverse matrix. I'm changing colour so I don't meld everything into each other. Determinant of C. So we've got our C matrix being 8, 2, 8, 2. A times D, these guys here, is 8 times 2. And then we do B times C, which is 8 times 2, and we subtract them. 16 takes 16 equals 0. Now part 2 says the inverse if it exists. since the determinant of C equals 0, C to the negative 1 does not exist. All right, moving on to the next slide. This gets a little bit trickier. We start to bring a touch of algebra in here. Don't be overwhelmed by it. It's actually not too challenging. If the determinant of 5 negative 3x3 is equal to 21, what is the value of x? Now we remember the formula for the determinant. Determinant is equal to AD minus BC. So what we do is we substitute in. We go 5 times 3, take away negative 3 times x. So I've got 15 take negative 3x. Now, remembering when I've got my two negatives here, becomes a positive. So it's equal to 15 plus 3x. Now, this determinant is equal to 21. So I need to substitute in that 21. So 21 is equal to 15 plus 3x. I'm going to scratch that out and make a little bit more room. So we need to get all the pronumerals on one side and all the constants on the other. So what I'm going to do is I'm going to get rid of this guy here. So I'm going to subtract 15 from both sides. And I end up with 6 is equal to 3x. Now I need to get rid of this 3. So I'm dividing both sides by 3. And I get 2 is equal to x. So my final matrix would be 5 minus 3, 2, 3. It didn't ask me to write out the matrix, but I'm just popping that back in there. All right, last problem. It is a longer problem, but it is our last problem. For the matrix A equaling 3, 2, x negative 3, what is the value for x for which A is equal to A to the negative 1? So that means that both the matrix and the inverse are equal to each other when we know the value of x. So first of all, we need to find our determinant. So determinant for A is equal to AD minus BC. So we've got 3 times negative 3, take 2 times x. So at the moment we've got negative 9, take 2x. All right, that's easy enough. To find the inverse, we need to put our determinant under a fraction. So negative 9 minus 2x. You're starting to think, far out, this is a lot of work. Yes, it will be, but it's actually not that bad. Then we switch our positions. So we switch our A and D, so negative 3 and 3, and then we make our 2 and our x negative. Oops, forgot my negatives. All right, then I just multiply through. So I multiply the 1 over negative 9 minus 2x through every element within this matrix. So I end up with negative 3 over negative 9 minus 2x, negative 2 over negative 9 minus 2x. Now I'm not simplifying or anything, I'm not changing anything, I'm just keeping it as it is. Negative x over negative 9 minus 2x and 3 over negative 9 minus 2x. Do not change signs, do not do anything, don't change anything, just leave it as is. Okay, we're halfway there. So we found our inverse of A. Now we need to solve for x. There's a lot of x's in here. Where do we start? Now, I'm going to skip to the next slide and I'm going to rewrite that out again. And remember, that A is equal to A inverse. We found that out in the last slide. It actually stipulates in the question. All right, so we know that 3, 2, x negative 3 is equal to negative 3 or negative 9 minus 2x. I could have just cut and pasted. X and 3 negative 9 minus 2x. All right, box around those. Now, for matrix A to equal matrix B, or A to equal A inverse, we know that each element has to be equal. And it says solve for x. I'm not going to use this x down here in that first matrix. I'm going to use one of the already determined numbers. And because A equals A inverse, each element equals each other. So that means that 3 is actually equal to negative 3 minus 9 minus 2x. Then all I need to do is solve for x. So where's my red pen, that one? So I times both sides by negative 9 minus 2x. Oops, let me just write that neater. Negative 9 minus 2x gives us 3 negative 27 minus 6x is equal to minus 3. Now I'm going to add 27 to both sides to get rid of this guy here. Oops, I need blue. So I've currently got minus 6x equals 24. Then divide both sides by minus 6. And I end up with x equals minus 4. So even though I had one very, very confusing looking matrix with the inverse, it managed to solve such that I managed to solve it with just using two similar elements or two elements in the same position. So my original matrix will then look like 3, 2, negative 4, negative 3. I'm not going to solve it, but that's what my x value is, and I've just substituted that back into A. And we're done. Now, feel free to ask any more questions if you need clarification about inverse matrices. It's probably, out of all of this chapter, probably the most trickiest thing to get your head around. Once you grasp that, you'll be fine with the rest. It gets easier from here. See you back soon for 7.5.